This time on Battle Factory. Carried to safety on a bed of shock-absorbing springs. A medal that commemorates supreme sacrifice. Jumping out of a plane when the drop zone is a combat zone. And a lightweight fighting vehicle gears up with heavy firepower. Battle Factory steps beyond the front lines into top secret factories where combat gear is built for battle. Stitching these sheets of lightweight material together can create an air-resistant canopy that can drop a fighting force out of the sky and turn the tides of war. When Leonardo da Vinci first conceived of the parachute in 1483, he may not have realized the impact it would have on warfare. 5 centuries later, the Allies launched Operation Varsity. On a single day in March 1945, 16,000 British and American infantry were dropped onto the eastern banks of the Rhine, securing strategic towns and bridges and playing a pivotal role in the Allied victory. The RS-2000 military parachute breaks down to the chute pack, the harness, and the canopy. It takes 90 meters of tear-resistant material to create the parachute canopy. The idea of a parachute is simple. A canopy traps a large volume of air, creating enough resistance to dramatically reduce your terminal velocity. So you can jump out of a plane and land softly on the ground. But the design of a parachute is actually quite complex. The RS-2000 is made of 2 types of nylon, airtight and porous, which lets some of the air through. Hundreds of individual panels of both fabrics are laid out, measured, and machine cut on a diagonal. This prevents any rips or holes that might occur from spreading while in use. The panels are sewn together into 7-meter wedges. The combination of airtight and porous panels help to soften the tug of the canopy opening and stabilize it during descent. Nylon tape is used to ensure the seams are tight. A rip in the air could prove fatal. Then they are laid across a light table. Every seam is meticulously checked to make sure they overlap perfectly and will hold under pressure. The wedges are sewn together and the seams are checked again. It takes 30 of them to create the parachute canopy. A circular vent is left open at the top of the parachute. This vent prevents the canopy from opening too fast and too hard and jerking on the harness with a painful jolt. The suspension lines are what connect the canopy to the jumper's harness. Each parachute requires 30 lines, which are cut into 9-meter lengths and pinned into place. Then, they're sewn into the parachute's nylon seams. Once the parachute is complete, it's blown open with compressed air. Every seam and fitting is inspected before the canopy is folded up and put inside the chute pack for deployment. The harness is what suspends the jumper from the canopy. It's made from very strong nylon strapping that is measured and cut with a heat knife to prevent the ends from fraying. The strapping is secured together with a series of buckles and clips to make an adjustable harness that loops around the shoulders and legs. On an airborne mission, paratroopers typically jump from low altitudes to minimize exposure to enemy gunfire. For safety and simplicity, the chute opens automatically moments after the jumper leaves the plane. A 4.5-meter yellow static line runs from the cable on the plane to the jumper's chute pack. When he drops past 4.5 meters, the static line opens the pack and frees the canopy. Next time this chute sees daylight, it could be a kilometer above the ground. And every paratrooper who steps out of a plane is taking a leap of faith that his chute is going to let him down easy. Coming up on Battle Factory, a stretcher that suspends the victim in comfort and security, and a medal to honor those who gave everything in service of their country. These simple springs aren't just designed for a pleasant ride. The Yellow Jacket basket's unique shock-absorbing suspension will protect a victim who's already in trouble from further injury. In search and rescue, getting the victim swiftly and safely to medical attention is critical. But sometimes the stretcher, which consists of 2 poles and a piece of canvas, does more harm than good. Now, the Yellow Jacket is the paramedics' answer to an age-old problem. The stretcher breaks down into the shell, the springs of the insert, and the frame. The first step in building the frame is to measure out lightweight aluminum tubes. It takes 41 precision-cut pieces to construct the stretcher frame. Each piece is bent into shape on a digital pipe bender. Every angle is programmed into the press so that every piece fits together. Then, the 2 largest rods are hammered together to make up the outside edge. Next, it's placed on a jig, an adjustable device that locks all the pieces in place so they don't budge while being welded. Once everything is locked down, the frame is welded together. The yellow basket was inspired by a rescue gone wrong. A construction worker had fallen into a deep pit and broken his leg. Firefighter Ian Bassendale was among the first responders to haul the victim out. They eased him into a conventional stretcher and strapped him in with ropes. On the way up, the victim slipped, causing a simple fracture to become a painful compound fracture. Bassendale vowed to build a stretcher that would keep a patient secure and safe, no matter how steep the rescue. The shell is a lightweight innovation that keeps the patient secure at any angle. The super tough plastic can withstand extreme cold and heat, and can take a beating being dragged over rocks and snow. Holes are cut into the pre-made shell so that it'll fit snugly onto the frame. The stretcher bed is cut from extremely durable nylon reinforced vinyl. The pieces are stitched together using tough nylon thread. The innovative belt system is designed so the victim can be transported securely at any angle. And each of the belts is tested to 5,000 pounds. So once you're buckled in, you're not going anywhere. Before the yellow basket, it took 45 minutes of lashing with rope to prep a victim for an aerial rescue. Now it takes just minutes to secure the passenger for an airlift. The spring system is what gives the stretcher its unique shock-absorbing capacity, and the difference between a safe ride and a potentially damaging one. 10 individual springs secure the bed to the aluminum frame. The springs are distributed around the frame to maximize shock absorption, doubling up at the head and hip area, where the patient is heaviest and most likely to be hurt. The stretcher can take the weight and take the hit. Finally, the stretcher is then lowered onto the shell and clipped into place. The Yellow Jacket stretcher has revolutionized the rescue process for over 5,000 first response agencies and military organizations around the world. ensuring that the trip to safety is a success. Coming up on Battle Factory, awarding the highest honor for the greatest loss, and the business end of the Stryker armored vehicle. These 1,000-ounce bars of pure silver bullion can be worth tens of thousands of dollars apiece. So one pallet alone can be worth over $1 million. But some of Canada's bravest have paid a much higher price. The Sacrifice Medal was created in 2008. And today it's been awarded to 780 Canadians wounded or killed in the service of their country. In Afghanistan in 2007, a deadly IED blast wounded a young soldier named Simon Mayou. As a result, his left leg had to be amputated. 2 years later, Simon was awarded the Sacrifice Medal and became the first Canadian amputee to be returned to active duty. He flew out the very same night as his medal ceremony. The medal is manufactured at the Royal Canadian Mint in Canada's capital city, Ottawa. Over $1 billion worth of precious metal is stockpiled here. So armed guards and closed-circuit cameras track every movement inside the mint. From the metal design to engraving the die, creating the Sacrifice Medal requires skill and care. The Sacrifice Medal breaks down into the ribbon, the suspension, and the medal. Using a design approved by the Queen in 2008, the front side of the 3.5-centimeter disc is engraved with the image of Queen Elizabeth II, the head of state and the armed forces. On the reverse is the statue Canada from the Vimy Ridge Memorial, the symbolic mother of a nation grieving for her fallen. The digital image is transferred onto a steel die and used to strike the Sacrifice Medal. The bars of fine silver that will make up the medal are lined up in a conveyor belt and carried into a machine that cuts them into thirds so they'll fit into the casting furnace. Then they're hand-fed into the furnace, which reaches 1,250 degrees Celsius, in order to turn the precious metal to molten silver. The silver comes out in water-cooled slabs, about 13 centimeters wide and various thicknesses. Then, the shiny strip is wound into 450-kilogram coils, about 2.4 meters long. In the rolling room, the coil is unspooled and rocked back and forth to thin out the slab to a higher gauge. To keep the silver soft, it's reheated in another furnace at 500 degrees. It's put back on the roller, and finally the silver strip is thin enough for the basic shape of the metal to be punched out. A blank is then prepped for striking. It's blown clean and placed in the press. During the striking process, the die strikes the design onto both sides of the silver disc with several hundred tons of pressure. Once the metal is struck, it goes into a mill where the edges are shaved smooth. A hole is drilled in the bracket, and the suspension, which will hold the ribbon, is attached. Before being awarded, the medal is suspended on a multicolored ribbon. The red stripe is symbolic of spilt blood, the black symbolizes loss, and the white stripe represents hope and peace. For soldier Simon Mayou, going back to the battlefield didn't just take courage. He had to prove he'd overcome his disability, marching 14 kilometers on his artificial limb, digging a foot-deep trench, and carrying a fellow officer for 100 meters. Soldiers like Mayu, those who made it back, those who didn't, are emblematic of the bravery, the service, and the sacrifice that merit the Sacrifice Medal. Coming up on Battle Factory, 1 cannon, 4 kinds of ammo, and a round every 6 seconds. This tube of forged steel will be hammered into one of the most powerful and famous cannons in modern warfare. Today, the M68 105mm cannon sits on the turret of a Stryker armored vehicle, but it's a cannon with a long and storied history. During the Gulf War, the 105 was mounted on the turret of a Patton M60 battle tank. In February 1991, the 1st Marine Division spearheaded the liberation of Kuwait. It looked like the advance would be uncontested until the Iraqis attempted a daring counterattack. The Americans, in Patton M60 tanks armed with 105mm cannons, were forced to go head-to-head against hundreds of Saddam's tanks and armored vehicles. Over 20 years later, this cannon is still a force to be reckoned with. A battle tank is only as effective as its gun, and for the Stryker vehicle, that's the M68 105mm cannon. First, a block of gun steel is heated in a furnace for an hour at 2,000 degrees to soften the metal. Then, a jaw-like mechanism called a chuck grabs the tube and pushes it into the rotary forge. In the forge, 4 synchronized hammers strike the tube with 200 tons of force. As the hammers pound at its surface, the tube rotates. This process lengthens and shapes the red-hot metal as if it were clay. Coming out of the forge, the cannon has stretched in length from 3.3 meters to 6.8 meters. The cannon is lifted onto cooling racks to cool for 24 hours. Then the cannon is reheated in another oven with open flame for about an hour and then cooled with water. This process hardens the steel. After all this heating and cooling, the cannon develops bends. A shell launched from a warped cannon will veer off its target and might even misfire. To straighten the cannon, it's hoisted onto a vertical press. The tube revolves while a probe measures it, and the operator marks any warps. Next, 1,000 tons of pressure is applied to the areas that are warped, and the cannon is made perfectly straight. During the Gulf War liberation of Kuwait, Saddam's tank units launched a fierce attack against the U.S. troops. They responded with force. The Patton M60 was a superior tank, and the 105mm cannon meant the Americans could get shots off from 2 kilometers away, outgunning the Russian-supplied T-64s. Hours later, the Iraqi arsenal lay in ruins, while the Americans didn't suffer a single loss. This marked the end of Saddam's occupation of Kuwait and the beginning of its liberation. First, the cannon spends 6 hours rotating on a lathe. It machines off the rough exterior metal called bark, leaving behind a shiny, clean finish. Next, a machine drills through the length of it to make the inside opening of the barrel wider. Then, it is honed by rotating grinding stones inside the cavity to smooth it out and bring the barrel close to size. Synthetic oil reduces the extreme heat and friction. When it's finished, the diameter will be exactly 105 millimeters, the measurement that gives this cannon its name. Once the inside has been smoothed out, the cannon barrel is checked for cracks and imperfections. The interior is brought to spec, and the breech end of the cannon is threaded so it can be attached to the tank. Finally, the cannon is rifled. Helical grooves are carved onto the inside walls of the barrel, which causes the shell to spin when it fires. This stabilizes its trajectory and improves the aim. By the mid-1980s, the 105mm cannon ceased to be the largest tank cannon out there when the M1 Abrams was built. But the 105 is still a force to be reckoned with. These days, it does duty on the top of a Stryker, an armored fighting vehicle. And with the 105mm cannon riding up top, it now wields the power of a battle tank. This time on Battle Factory. The military menu that feeds the fight. The weapon that puts flexible firepower in the soldier's hands. And get the real feel of flying without ever leaving the ground. Battle Factory steps beyond the front lines into top secret factories where combat gear is built for battle. This packet contains enough food energy to keep a soldier fueled for the fight. The MRE, or Meal Ready to Eat, is a nutritious food ration distributed to servicemen and women in the field that can be heated on site in mere minutes. 100 years ago, dinner in the trenches of World War I wasn't as appetizing. Due to short supplies of staples and poor preservation, British troops subsisted on thin soups flavored with mystery meat, canned corned beef, and bread substitute made from dried turnips. Tins of sugary tea masked the flavor of water transported in gas tanks. Today, combat meals have been replaced by the MRE. The MRE breaks down into the flameless ration heater, the pouch of water, and the meal bag. The meals ready to eat must be prepared in a sterile environment to prevent bacterial contamination. One recipe is made at a time in an industrial kettle. First, the pre-cooked ingredients are brought to the kettle. Today on the menu, chicken with barbecue sauce, black beans, and potatoes. The preheated barbecue sauce, fortified with extra vitamins and minerals, is pumped into the kettle. Then the ingredients are poured into the sauce and mixed. Frozen chicken, dehydrated potatoes, and black beans. The MRE is health food and haute cuisine compared to the C rations of World War II. The C stands for combat, but it might as well have stood for canned. Canned meat, canned bread, and canned dessert. Affectionately known as C rats, they were only intended to feed a GI for a few days before being supplemented with real food. But toward the end of the war, C rations were all they got. By the late 1950s, the Army accumulated such a large stockpile, they were able to feed soldiers these temporary meals right through the Vietnam War. The meal bags are made from a combination of strong, flexible plastic and metal foil, making them highly durable and puncture resistant. The barbecue chicken meal is now pumped through a reservoir at the filling machine. The meal bags travel along a conveyor system where they're stamped with the ingredients, the plant number, and the date of production. Then, each bag is blown open with air jets, and the 228-gram meal is pumped into each bag. Each kettle can produce 1,400 meal bags every 20 minutes. Before being sealed, the bag is blasted with air to make sure no food is blocking the mouth of the bag. Then, the bag is heat sealed. An 8-hour shift can produce up to 100,000 meal bags. By the time the World War II C rations had arrived in Vietnam in the late 1960s, they were over 20 years old. And because the paper label often slipped off, Every meal was a surprise. Today, MRE menus include Asian and Caribbean dishes, and there's even a vegetarian option. When the packages arrive at quality control, they are X-rayed for impurities, and every batch is sterilized and monitored. Samples are put into testing bags and sent through a sterilization chamber along with the rest of the batch. The monitors track the exact temperature, ensuring that the contents of the meal will be safe when reheated in the field. If a soldier gets sick to his stomach on the battlefield, he's at risk to himself and a liability to his squad. So food in the combat zone needs to be plentiful and safe. Every MRE contains 2 entrees and 2 sides, like high-energy bars and drink crystals, for a total of 1,300 calories. The packages also contain a pouch of water and 2 plastic bags called the flameless ration heaters. The bottom of the bag is a package containing magnesium mixed with metallic iron particles and table salt. Adding water causes a chemical reaction that heats it until it boils. The meal bag is inserted and left to heat, and the meal is ready to eat in 10 minutes. The final step is to seal the bags with cutlery and napkins. Then they can be packed and ready to ship to the field. War is no picnic, but if an army really does travel on its stomach, the MRE is the fuel that gets them to the front lines. Coming up on Battle Factory, a weapon with 150-meter range that doubles the fighting power. And climb aboard this craft, and you can take off without a runway or an airplane. Using the latest technology, these harmless bits of plastic will be melted and molded to create a snap-on weapon that drastically increases the firepower in a soldier's hands. The M203 grenade launcher is a single-shot launcher designed to attach under a rifle barrel. In World War I, the original grenade launchers were the infantrymen themselves, who both lit and lobbed the mini-bombs from the trenches. They could throw the grenade 15 meters fairly accurately, but would have to duck for cover to avoid the shrapnel from the explosion. The Leach Trench catapult was the first attempt at a solution, sending the grenades as far as 200 meters, but the aim was iffy. Today's version has both range and precision. The M203 grenade launcher breaks down into the barrel, the hand grip, and the receiver. The receiver of the grenade launcher is what contains the firing mechanisms, houses the barrel, and connects the launcher to the rifle. It starts off as a block of aluminum that's precision cut on a CNC, or computer-controlled machine. Once cut, the probe calculates the exact measurements to make sure that every dimension is to spec. It was originally designed to fit on the M16 rifle, but is currently compatible with many rifle models. Once the receiver is passed inspection, it's engraved with a serial number and registration code for security and quality control. Next, the receiver is anodized. The aluminum is dropped in an acid bath and charged with electricity, which alters the property of the metal surface, making it harder and rust-resistant. Once the receiver is treated, its moving parts can be added. First, the barrel latch locks the barrel and receiver together. Then the barrel stop goes in to prevent the barrel from sliding off the receiver during loading and cocking. Next comes the firing mechanism. The firing pin and cocking lever are inserted into the receiver and held in place with a locator pin. Then the safety, the trigger, and the trigger guard are installed, and the receiver is complete. World War II saw the advent of a rifle grenade that worked like a mortar and could travel 140 meters. A rod attached to the bottom of the grenade loaded into a standard rifle barrel. This crude launcher damaged the rifle and compromised its utility. Today, the modern grenade launcher doesn't damage the barrel since it's slung underneath, turning the gun into a double-duty weapon. With the hand grenade, once you remove the firing pin, you had 4 seconds to throw and run. The modern grenade launcher arms and detonates its payload differently. When the grenade is launched, the centrifugal force of the spinning missile arms the fuse. When the grenade hits the target, the firing pin is pushed back into the percussion cap, sparking an ignition, so that the grenade explodes on contact. The hand grip is a molded plastic sleeve that slides over the barrel for easy loading and protects the operator from burns. The grip is made by injection molding. Plastic granules are suctioned into the hopper, piped into the molding machine, and injected into the mold. The combination of heat and friction liquefy the plastic. Once the plastic is set, the mold opens and expels the hand grip. By the 1950s, the U.S. military had developed the M79, a purpose-built grenade launcher that looked like a shotgun with a huge barrel. These were used in Vietnam, but once the soldier was out of grenades, all he had left to defend himself was his small sidearm. So the U.S. military developed the M203 to fit on the M16 rifle. The launcher barrel is constructed of the same specially treated aluminum and is attached to the receiver. When the launcher is assembled, it gets a full function check to ensure the barrel latch and stop are doing their jobs. Finally, the receiver assembly is attached to the rifle barrel, and the M203 grenade launcher is ready to deploy. With the M203, the soldier can switch between weapons in seconds and engage targets that can't be reached by direct fire, converting a rifle from a weapon into an arsenal. Coming up on Battle Factory, the only airplane you can crash and reboot. It takes 12 months and millions of parts to create this structure that stands 9 meters high. But once inside it, you'll believe you're 9 kilometers in the air. Inside the cockpit of the CAE flight simulator, every nerve ending tells you you're flying, from the feel of the controls to the view out the window and the thrust of the G-force. In the military, by the time a pilot climbs into the cockpit of a real airplane, he's already had many hours of operational flying time without ever leaving the ground. It wasn't always this way. Prior to the advent of the flight simulator, learning to be a fighter pilot was actually more dangerous than flying combat missions. In World War I, 2 cadets were killed during training for every flyer killed in battle. Every simulator costs millions of dollars to make, but it's worth every penny. The CAE flight simulator breaks down into the motion control, the platform, the outer shell, and the flight controls. The flight control unit makes up the bottom part of the cockpit and houses the gears that control the flying movements the flight simulator makes, like thrust, pitching, and banking. The flight control unit and its many gears are milled from aluminum. The pieces are all modular and fit together like a complicated puzzle. The gears will eventually be connected to the hand levers on the control panel, the side stick, and overhead panel. They have resistance built into them to simulate the authentic feel a pilot experiences when driving the gears and controlling the aircraft. And every simulator is custom built to replicate a specific model of airplane, from civilian passenger jets to military fighter planes. The first simulator was developed by Edwin Link in the 1920s. He was an amateur flyer with a first-hand knowledge of engineering, electronics, and pneumatics from his family's pipe organ factory. He offered his Link trainer to the U.S. government in 1929, but they dismissed the concept entirely. The avionics panel contains the buttons, displays, and instrument panels that control the engines and navigation systems. Because every model of aircraft looks and flies differently, every simulator's avionics panel is a customized copy of the airplane it's meant to replicate. 3D printers generate buttons, knobs, and handles that ensure that the simulator's interface will look, feel, and function exactly like the model of plane that the trainee pilot will fly in the real world. Over 30 kilometers of cable are cut, identified, and thread into the panel. It takes hundreds of hours to do the intricate wiring. One error would cause the aviation panel to short circuit. Next, the brains of the cockpit, the circuit boards, are assembled. A programmed robotic machine grabs the tiny circuits and drops them in the slots on the circuit boards. Then, they're passed through an oven, and the circuits are fused onto the panel. There are hundreds of printed circuit boards in every simulator, performing thousands of operations per second. Today, flight simulators are a first option for training commercial and military aviators, but they got their start on the heels of a tough and tragic lesson. In 1934, Franklin D. Roosevelt recruited the U.S. Air Force to deliver airmail across America. Flying an aircraft that had been used in World War I, the pilots were given a civilian mission very different from their wartime experience. Pilots had to contend with stormy weather and unfamiliar airstrips. In the first disastrous month of the program alone, there were 66 crashes. The nation responded to this tragedy with an outcry. Roosevelt realized something had to be done. Coming up on Battle Factory, President Roosevelt turns to an unlikely source for help. In 1934, in the first few months of delivering the mail by air, the newly commissioned U.S. Air Force pilots were crashing all over the country. In desperation, Roosevelt and the Air Force reached out to the same person that had been rejected years before, Edwin Link. 6 Link trainers were ordered immediately. By the time World War II broke, there were 10,000 flight simulators in service. The cockpit module sits on top of the flight control unit and gives the interior of the simulator the look and feel of the inside of an aircraft. Built-in speakers broadcast everything from the roar of takeoff to the thunk of landing gear being deployed. Once the module is completely outfitted, it's raised onto the carriage and secured. The rest of the interior components are installed. The panels and doors of the platform are made from heavy-duty aluminum to handle the stress of the 10,000-kilogram simulator bouncing around for the next 20 years. The sheets of metal are cut and sent to a punch press that cuts the aluminum into various shapes and then bent. Then the components are assembled, painted airplane white, and baked to a hard finish. Once finished, the platform is attached to the flight control unit and the cockpit module. The simulator is capable of its unique movement because of the design of the bearings, which act like joints. They work together to choreograph an aircraft's 3 planes of motion: pitch, front to back motion, yaw, sliding on the vertical axis, and roll, tipping from side to side. Each of the bearing houses are made from aluminum and injected with grease to keep them lubricated. Each bearing will hold a leg known as a jack at either end, which allows the flight simulator to rock and roll. The visual bowl of the simulator, which is made out of fiberglass and aluminum, stands in for the cockpit window. The ever-changing visuals are projected onto a curved mylar screen, giving the pilot in training 180 degrees of virtual landscape. In the late 1950s, simulators would use film projection of scale model terrains, and then in the 60s, advanced to TV screens outside the cockpit. By the early 70s, computers were generating crude digital skyscapes. Today, the difference between a simulated and real cockpit is virtually indistinguishable, and the sophisticated flight programs can throw any dangerous scenario at the trainee. Extreme weather, equipment failure, emergency landings, and combat scenarios. 80 years after the first mail delivery disaster, pilots are required to do hours of simulator training. So by the time they climb into the real cockpit, they won't be winging it. Because once you've flown a simulator, you're ready to take off in the real thing.